international scientific culture. Computer science was later added to the mix, and the centre was duly renamed Centrum Wiskunde en Informatica, or in short, CWI. CWI researchers work at fundamental, groundbreaking research that lays the foundation for future breakthroughs. The CWI strives to share the knowledge it acquires with society, and its research therefore always has a social relevance. This has proven itself repeatedly over the years. Let's take a look at some of the research. In 1952, the Mathematical Centre developed the first Dutch computer, ARA. After the North Sea flood disaster in 1953, which killed nearly 2,000 people in the Netherlands, ARA was used to create models and perform calculations for the Delta Works, the Dutch national plan for new water defences, to prevent such a flood happening again. Today, the Delta Works still protect the Netherlands against high water. Cooperation is central in how CWI works, both on a national and international level, with companies and with individual researchers, who themselves go on to launch spin-offs. The first CWI spin-off was in 1956, Electrologica, the first Dutch computer manufacturer. To date, there have been 27 spin-offs. A modern example is Stockhos, that makes software that predicts how ambulances can be efficiently distributed within a region and therefore be on the scene faster, a literal life-saving development. Navigation is an integral part of daily life. In 1959, one of the world's top computer scientists, Edske Dijkstra, developed the shortest path algorithm, also known as Dijkstra's algorithm. This is the basis of all route planners used today. For those who do not like to navigate but prefer travelling by train, CWI has also delivered. In 2007, CWI researcher Lex Schrijver, with others, created an algorithm that was used to redesign and optimise the timetables of the Dutch railways. For his CWI research, Lex received the Spinoza Prize, the highest Dutch science award. For most of its 75 years, CWI has been a hotbed of programming language design and development, starting with the algorithmic languages Algol 60 and Algol 68, and continuing with Python, developed in 1989 by Guido van Rossum. Python is now the #1 programming language in the world and has millions of users, from hobby programmers to tech giants like Google, Amazon, Yahoo, and Facebook. CWI has also been a leader in the development of the internet. In April 1986, CWI registered .nl as one of the first country domains worldwide, followed by the first Dutch domain name, CWI.nl. Not long after that, in November 1988, CWI set up the first node on the open internet in Europe and spun off 2 companies to further expand the internet in the Netherlands and Europe. CWI was involved right from the beginning with the internet's most important application, the World Wide Web, and had one of the world's first websites. CWI researchers have contributed to the design of many web standards, including CSS, HTML, XHTML, SVG, RDF, and many others. For security and privacy on the web and the internet, data is usually encrypted. CWI has always been on the forefront of research in encryption, both in creating encryption methods and in testing them by attempting to break them. In 1999, CWI coordinated the breaking of the encryption standard RSA 512 by factoring large numbers into their prime factors. In 2008, a group of CWI researchers and international colleagues exposed weaknesses in the MD5 security standard, which is widely used on the internet, for example, by web browsers. In 2017, the same happened again with the security standard SHA-1, which is used to protect credit card transactions and digital signatures. In the near future, quantum computers will surpass ordinary computers in performance. What will the possibilities be, and how can they best be used? In 2015, CWI launched QSoft, the Research Centre for Quantum Software. Within QSoft, researchers explore the possibilities and limitations of software that could be used on such computers once they are available. In addition, quantum research also contributes to the development of artificial intelligence. Also in 2015, the CWI opened the FlexRay lab with its unparalleled X-ray scanner that provides real-time 3D images. With the FlexRay lab, mathematics and 3D scanning are brought together, so the new calculation methods can immediately prove themselves in practice. Working closely together with radiotherapists, CWI developed artificial intelligence to realize improvements in radiation treatment for cancer. Patients are now treated following optimal radiation plans created by AI. CWI also works on energy research, with the main questions being, how do you achieve the most with artificial intelligence and calculation models from available energy sources? And how do you distribute energy fairly and efficiently? Throughout its history, CWI has been an innovator, connector and driver in mathematics and computer science, joining forces with the best and most motivated scientists and organizations in the field, and with unprecedented future possibilities ahead, they will continue to expand their work. This year, the CWI is celebrating. 75 years ago, the Institute opened its doors under the name mathematician or mathematical center. Its aim was to promote the use of pure and applied mathematics in the reconstruction of the Netherlands after the Second World War, to improve prosperity in the Netherlands and to enhance the Dutch contribution to international scientific culture. Computer science was later added to the mix, and the centre was duly renamed Centrum Wiskunde en Informatica, or in short, CWI. CWI researchers work at fundamental, groundbreaking research that lays the foundation for future breakthroughs. The CWI strives to share the knowledge it acquires with society, and its research therefore always has a social relevance. This has proven itself repeatedly over the years. Let's take a look at some of the research. In 1952, the Mathematical Centre developed the first Dutch computer, ARA. After the North Sea flood disaster in 1953, which killed nearly 2,000 people in the Netherlands, ARA was used to create models and perform calculations for the Delta Works, the Dutch national plan for new water defences, to prevent such a flood happening again. Today, the Delta Works still protect the Netherlands against high water. Cooperation is central in how CWI works, both on a national and international level, with companies and with individual researchers, who themselves go on to launch spin-offs. The first CWI spin-off was in 1956, Electrologica, the first Dutch computer manufacturer. To date, there have been 27 spin-offs. A modern example is Stockhos, that makes software that predicts how ambulances can be efficiently distributed within a region and therefore be on the scene faster, a literal life-saving development. Navigation is an integral part of daily life. In 1959, one of the world's top computer scientists, Edske Dijkstra, developed the shortest path algorithm, also known as Dijkstra's algorithm. This is the basis of all route planners used today. For those who do not like to navigate but prefer travelling by train, CWI has also delivered. In 2007, CWI researcher Lex Schrijver, with others, created an algorithm that was used to redesign and optimise the timetables of the Dutch railways. For his CWI research, Lex received the Spinoza Prize, the highest Dutch science award. For most of its 75 years, CWI has been a hotbed of programming language design and development, starting with the algorithmic languages Algol 60 and Algol 68, and continuing with Python, developed in 1989 by Guido van Rossum. Python is now the #1 programming language in the world and has millions of users, from hobby programmers to tech giants like Google, Amazon, Yahoo and Facebook. CWI has also been a leader in the development of the internet. In April 1986, CWI registered .nl as one of the first country domains worldwide, followed by the first Dutch domain name, CWI.nl. Not long after that, in November 1988, CWI set up the first node on the open internet in Europe and spun off 2 companies to further expand the internet in the Netherlands and Europe. CWI was involved right from the beginning with the internet's most important application, the World Wide Web, and had one of the world's first websites. CWI researchers have contributed to the design of many web standards, including CSS, HTML, XHTML, SVG, RDF, and many others. For security and privacy on the web and the internet, data is usually encrypted. CWI has always been on the forefront of research in encryption, both in creating encryption methods and in testing them by attempting to break them. In 1999, CWI coordinated the breaking of the encryption standard RSA 512 by factoring large numbers into their prime factors. In 2008, a group of CWI researchers and international colleagues exposed weaknesses in the MD5 security standard, which is widely used on the internet, for example, by web browsers. In 2017, the same happened again with the security standard SHA-1, which is used to protect credit card transactions and digital signatures. In the near future, quantum computers will surpass ordinary computers in performance. What will the possibilities be, and how can they best be used? In 2015, CWI launched QSoft, the Research Centre for Quantum Software. Within QSoft, researchers explore the possibilities and limitations of software that could be used on such computers once they are available. In addition, quantum research also contributes to the development of artificial intelligence. Also in 2015, the CWI opened the FlexRay lab with its unparalleled X-ray scanner that provides real-time 3D images. With the FlexRay lab, mathematics and 3D scanning are brought together, so the new calculation methods can immediately prove themselves in practice. Working closely together with radiotherapists, CWI developed artificial intelligence to realize improvements in radiation treatment for cancer. Patients are now treated following optimal radiation plans created by AI. CWI also works on energy research, with the main questions being, how do you achieve the most with artificial intelligence and calculation models from available energy sources? And how do you distribute energy fairly and efficiently? Throughout its history, CWI has been an innovator, connector and driver in mathematics and computer science. Joining forces with the best and most motivated scientists and organizations in the field, and with unprecedented future possibilities ahead, they will continue to expand their work. This year, the CWI is celebrating. 75 years ago, the Institute opened its doors under the name mathematician or Mathematical Centre. Its aim was to promote the use of pure and applied mathematics in the reconstruction of the Netherlands after the Second World War, to improve prosperity in the Netherlands and to enhance the Dutch contribution to international scientific culture. Computer science was later added to the mix, and the centre was duly renamed Centrum Wiskunde en Informatica, or in short, CWI. CWI researchers work at fundamental, groundbreaking research that lays the foundation for future breakthroughs. The CWI strives to share the knowledge it acquires with society, and its research therefore always has a social relevance. This has proven itself repeatedly over the years. Let's take a look at some of the research. In 1952, the Mathematical Centre developed the first Dutch computer, ARA. After the North Sea flood disaster in 1953, which killed nearly 2,000 people in the Netherlands, ARA was used to create models and perform calculations for the Delta Works, the Dutch national plan for new water defences, to prevent such a flood happening again. Today, the Delta Works still protect the Netherlands against high water. Cooperation is central in how CWI works, both on a national and international level, with companies and with individual researchers, who themselves go on to launch spin-offs. The first CWI spin-off was in 1956, Electrologica, the first Dutch computer manufacturer. To date, there have been 27 spin-offs. A modern example is Stockhos, that makes software that predicts how ambulances can be efficiently distributed within a region and therefore be on the scene faster, a literal life-saving development. Navigation is an integral part of daily life. In 1959, one of the world's top computer scientists, Edske Dijkstra, developed the shortest path algorithm, also known as Dijkstra's algorithm. This is the basis of all route planners used today. For those who do not like to navigate but prefer travelling by train, CWI has also delivered. In 2007, CWI researcher Lex Schrijver, with others, created an algorithm that was used to redesign and optimise the timetables of the Dutch railways. For his CWI research, Lex received the Spinoza Prize in Language Design and Development, starting with the algorithmic languages Algol 60 and Algol 68, and continuing with Python, developed in 1989 by Guido van Rossum. Python is now the #1 programming language in the world and has millions of users, from hobby programmers to tech giants like Google, Amazon, Yahoo and Facebook. CWI has also been a leader in the development of the internet. In April 1986, CWI registered .nl as one of the first country domains worldwide, followed by the first Dutch domain name, CWI.nl. Not long after that, in November 1988, CWI set up the first node on the open internet in Europe and spun off 2 companies to further expand the internet in the Netherlands and Europe. CWI was involved right from the beginning with the internet's most important application, the World Wide Web, and had one of the world's first websites. CWI researchers have contributed to the design of many web standards, including CSS, HTML, XHTML, SVG, RDF, and many others. For security and privacy on the web and the internet, data is usually encrypted. CWI has always been on the forefront of research in encryption, both in creating encryption methods and in testing them by attempting to break them. In 1999, CWI coordinated the breaking of the encryption standard RSA 512 by factoring large numbers into their prime factors. In 2008, a group of CWI researchers and international colleagues exposed weaknesses in the MD5 security standard, which is widely used on the internet, for example, by web browsers. In 2017, the same happened again with the security standard SHA-1, which is used to protect credit card transactions and digital signatures. In the near future, quantum computers will surpass ordinary computers in performance. What will the possibilities be, and how can they best be used? In 2015, CWI launched QSoft, the Research Centre for Quantum Software. Within QSoft, researchers explore the possibilities and limitations of software that could be used on such computers once they are available. In addition, quantum research also contributes to the development of artificial intelligence. Also in 2015, the CWI opened the FlexRay lab with its unparalleled X-ray scanner that provides real-time 3D images. With the FlexRay lab, mathematics and 3D scanning are brought together, so the new calculation methods can immediately prove themselves in practice. Working closely together with radiotherapists, CWI developed artificial intelligence to realize improvements in radiation treatment for cancer. Patients are now treated following optimal radiation plans created by AI. CWI also works on energy research, with the main questions being, how do you achieve the most with artificial intelligence and calculation models from available energy sources? And how do you distribute energy fairly and efficiently? Throughout its history, CWI has been an innovator, connector and driver in mathematics and computer science, joining forces with the best and most motivated scientists and organizations in the field, and with unprecedented future possibilities ahead, they will continue to expand their work.
It is my pleasure, as Director of CWI, the Dutch National Research Centre for Mathematics and Computer Science, to say a few words of welcome to all of you who take part in the Van Wijngaarden Award ceremony. In the very first place, I would like to extend a very warm welcome to our two special guests, the new laureates of the Van Wijngaarden Awards, Professor Marta Kwiatkowska and Professor Susan Murphy. Personally, I'm looking forward to hearing the both of you speak about your work later in tonight's program. A special welcome also to Professor Marcel Levi, Chair of the Dutch Research Council NWO, who will be presenting the laureates with the actual awards later in the program. And also a warm welcome to the two CWI researchers who will give the eulogy speeches, the so-called laudatios, CWI fellow Krzysztof Apt and CWI group leader Peter Grunwald. And obviously, I welcome all of you, CWI friends and CWI colleagues. Last but not least, welcome to the family members of the late Aad van Wijngaarden, who will follow tonight's ceremony via the live stream. Let me first say a few words about Aad van Wijngaarden. It was in his honor that CWI's 5 yearly awards were named. Aad van Wijngaarden was the influential and pioneering director of CWI. At the time it was called Mathematician for a period of 20 years, from 1961 to 1981. He has been involved in the Mathematician from the very beginning in 1946. Along with the post-war restructuring of the mathematical curriculum at the Dutch universities, one comprehensive mathematical center for research and development was established in Amsterdam. Van Wijngaarden was a young Delft Doctor of Engineering who was appointed head of the computing department of the new National Mathematisch Centrum. And over the years that followed, he grew into the founding father of computer science in the Netherlands, who helped shape computer science into an international endeavor. I find it especially fitting that a prize in his name honors the work of both mathematicians and computer scientists. Tonight is a celebration of the beauty of science and of the importance of science to society. But we celebrate this while the world is in turmoil. Worldwide, people struggle with the accessibility of electricity, oil and gas, basic necessities for heating our homes and producing goods for our daily lives. And a mere 2,000 kilometers to the east, a war is going on, the outcome of which will determine our lives for the next decade. Soldiers fight a life and death battle, and every day citizens are killed. I have heard some commentators mention the similarity with the Cuba crisis, one of the most peace-threatening moments since World War II, which happened to be when Aad van Wijngaarden just started as a director. I've asked myself, can we still celebrate the beauty of science in these circumstances? But yes, I think we can. And yes, I think we must celebrate science. Celebrate science for its own sake and because of the impact and relevance to society. I could give any number of examples of the way research in mathematics and computer science ultimately result in changing the world for the better. But I will not. Because tonight, dear guests, we are celebrating science and the beauty of science by focusing on two very special and eminent researchers, Marta Kwiatkowska and Susan Murphy, who we are about to honor with the Van Wijngaarden Awards. And therefore I invite CWI fellow Krzysztof Apt to the stage to present his eulogy to Marta Kwiatkowska.
Yes, so thank you for allowing me to say a few words about Marta, but I will start with somebody else. I was last summer in London and I visited... Sorry? Oh, sorry. Indeed. So I was last summer in London and I visited the Bank of England and made this photo of a £50 banknote with Alan Turing on it. This photo I stole from the internet. So in 5 minutes I'll explain to you what is the connection between these two individuals. So I'll start with the other individual, Marta. So I checked few facts about Marta. So she comes from a small village in southeast Poland, 3,000 inhabitants. Probably when you were born it was much smaller. Succeeded to find this charming photo of a wooden church which apparently burned down. Then Marta studied in Krakow, which, let me mention, is a university which is slightly older than the Leiden University. I once walked with Marta a few years ago to a venue where she was to give an invited talk, and she stopped in front of a building and said, "Can you wait a second in this?" And it was a very drabby, grey building. She said, "Here I shared a room with 3 other girls for 4 years." So these were the origins of Marta in Poland. And in 1980, she moved to UK and she eventually became a professor at the University of Oxford. So obviously she has some weakness for old universities. Now, let me return to Turing. So he wrote a paper in 1949 titled "On Checking a Large Routine." And this is a diagram taken from this paper in which a kind of flow chart was there with annotations. And this is usually considered to be the first serious attempt to come to grips with program verification. And then the history in a nutshell looks as follows, that sometime later, Robert Floyd in '67 formalized the idea how to verify programs which are expressible as flowcharts. 2 years later, Tony Hoare came up with an idea to deal with program verification in an axiomatic way. Marta, if you don't agree, please correct me. So far, so good, I hope. So Tony Hoare came up with an axiomatic method which could be extended to several classes of programs, which of course cannot be written as flowcharts. But this was a method which was based on logic. So you had to carry out proofs by hand, and correctness proofs are extremely error-prone. So then two groups of people independently came up with an idea of something which seems to be impossible to do automated program verification, and this technique became called model checking. Now, all people on this slide except one got Turing Award for their work, so this is just to give you an idea of the background. Now, model checking became possible because people realized that some programs, especially the concurrent programs or parallel programs with finite state, could be described formally and verified with some interactive way using fully automated tools. Now, the point is that this is a very limited class of programs, and here comes Marta. She has been working on probabilistic program verification for more than 20 years, and she came up with an idea of probabilistic model checking, which dramatically extended the scope of applications of this approach. And I now found that the system PRISM, for which she is most known, has been more than 20 years in development because the first paper dates from 2001. There was an error in the announcement because it was stated there that there were 80,000 downloads. I now checked, it's more than 93. And it is an impressive approach which is, has made program verification much more applied than the previous approaches, because Marta with her co-workers found that one could apply it successfully to several types of protocols, including industrial protocols, also multimedia protocols, but also what is important, to randomize algorithms and various protocols where the behavior is probabilistic. And what I notice is that she, with her co-workers, co-authors, continues this work, and this list keeps growing. Now, this looks like a listing of, let's say, applications, but I should add that all this is anchored in a very serious theoretical framework. And this framework combines methods from probability, using the Markov chains, and extended logics, which extend the previous approaches by adding probability, plus a system which apparently, which I find very impressive, has been growing for 20 years just as applications. I could have told much more about Marta, but I would be cut off, so I prefer to stop here. And thank you for your attention. Thank you.
Thank you, Krzysztof. Well, then I would like to invite Marta to the stage, but also Marcel to the stage to hand out the award. Yeah, and I would leave the stage to you.
Good evening, everyone. It's a fantastic pleasure being here and to be able to hand this fantastic, I haven't seen it before, but it looks very impressive, award to you, Marta Kwiatkowska. We were discussing actually earlier on during the evening that there is no Nobel Prize for for mathematics and computer science. So I hope you will consider this as kind of a surrogate Nobel Prize. At least we consider it as a surrogate Nobel Prize. I'm deeply impressed by your work. I'm not going to repeat everything that Krzysztof was saying. I have to say I worked in London for a couple of years, and my hospital was next to the Alan Turing Institute. And we managed to do some work with the people at that institute, which was actually absolutely fantastic. And I think it's a much bigger honor for someone like Alan Turing to have an institute rather than to be on a 50-pound note, which is not much worth anymore, as we all know nowadays. Having said that, I think your work is fantastic, and there is one thing I'd want to highlight. It was already mentioned that the work was almost 100,000 times the prison work, almost 100,000 times downloaded from the internet. It is open source. It is freely available for everyone who wants to use it. It is not for sale. People do not have to pay for it. I think it's the most fantastic example of what we all talk about: open science, open source, fair data, and that in itself would be a reason to award you that prize. But that's not the reason you get this prize. You get this prize for your fantastic research. Congratulations.
Okay. Thank you.
This is not as prestigious as the award, but as valuable. It's on behalf of
Thank you.
Okay. Thank you. You have to go with a picture as well? You? Yeah, why not? You're the for the laudatio. Oh, yeah.
Supposed to be on a picture.
Yeah.
So how about this? Oh, to you.
Yeah? Okay.
To the Polish Minister of Science.
Okay. Okay, Marta, congratulations on this award. As with many things, these tokens of appreciation also come with duties. In fact, with the Van Wijngaarden Award, there's only one duty, and that's that you have to give now a presentation. The floor is to you.
Okay. Good evening. It's great to be here, and of course, I'm very honored to receive this award. And, you know, especially after COVID, and given that this ceremony was supposed to happen last year, it is really wonderful to be giving this lecture in person rather than on Zoom. And for me, thank you for this opportunity to tell you about my research. I think, as Krzysztof has mentioned, you will see a little bit of this history in my lecture as well. It has been a significant effort, and it is something that I'm very happy to tell you about and share the experience. And I will focus, maybe because of the timing, you said not about the technicalities, but I'll say something about the applications and the lessons learned and what we can do with probabilistic model checking for a safer world. Right, so first of all, I'm a computer scientist, and this is really a very exciting time to be a computer scientist. So I'm showing you the pictures of robots. Robots, automation, AI, they are coming everywhere, and they seem to be taking over the world and taking over from us. They are taking over the tedious tasks, like perhaps watering plants. My husband is at home, and I know what he's done to plants in the past. But they are also taking over the dangerous tasks, such as testing motorcycles. But of course, the brains, robots that may be built by engineers, designed and built by engineers, but their brains are computer programs. And that's computer science. Now, computer science is also suffering because we are running out of space on silicon to put, you know, the billions and billions of processors that you need in order to power the AI and, you know, the digital economy. So what people are doing now is looking for alternative media, computational media. And one of those is molecular computing, and in particular DNA. DNA molecules can store information. We know that because, of course, they are the code of life, but they can also process information. If you take a number of strands, they can bind, and you can treat it as converting input signals into output signals. So a computer program is something that The Economist has described as computing with soup, because these DNA programs are put in a test tube, and you put the right number of strands of the right kind, leave them to it, and then they produce the output. And what the researchers have done at Caltech, they have already built even AI, even neural networks using DNA computing. So this is also very exciting. And of course, on top of that, there is deep learning with everything, you know, in face recognition, in medical diagnosis, in autonomous driving. But as every computer scientist and programmer will tell you, all these systems are plagued with a very, very old problem, programming errors. And already Babbage, who built mechanical calculators, he was obsessed with errors. And he was introducing schemes such as color coding and bells ringing, because computers, the reason this is in quotes, because computers were actually humans who were operating these machines. Ada Lovelace was working on a Bernoulli numbers program also for another of Babbage's machines, and she was trying to debug it and got frustrated, and in the end just went horse riding. Okay. Now, for us computer scientists, we know that there was a whole series of research that went into the design of programming languages, type systems to try to detect and prevent these errors. And you might think that, say, after 50, 70 years, the problem has been solved. But what I'm showing you there is, in fact, not, because if you think you are driving in an autonomous car that's actually using a neural network, you know, an AI system to perform vision, these are the kinds of errors that we now need to learn how to deal with. So, what do we do? Now, in fact, and I think as Krzysztof has already pointed out, these ideas go back to Turing. So Turing wrote this paper, and in fact, already Turing proposed the concept of assertions. You can see these assertions here in the flow chart. Now this then sparked off a lot of research, including Tony Hoare and Dijkstra, both of them Turing Award winners, to actually try to develop frameworks, mathematical frameworks, with which you can prove the program's correct. But my work fits more within this view, and rather than saying, okay, can we prove the program correct, what we are asking is, can we actually do it algorithmically? So can we run an algorithm that will prove the program correct? And this is the basic idea of model checking, and there are again Turing Award winners, Because on the one hand, to prove a program correct, you need to have a model of the program, but you also need to have a specification. So this started off with temporal logic, which is due to Amir Pnueli. Temporal logic was introduced in 1977, and it turned out that it was decidable. Decidable means that for finite state programs, you could actually run an algorithm. Okay, it may take ages, but the basic feasibility argument was there. And this is when Ed Clark came on the scene in the early 80s and developed the field of model checking, algorithmically checking whether the program does what it's supposed to do in a completely mechanical way. So mechanically just turning the handle as if it was, one of those Babbage's machines. But what I'm working on is probabilistic model checking. And probabilistic model checking means that I want to do model checking, but for probabilistic systems. Why? Well, because actually logic is not sufficient to describe the real world. And this is something that James Clerk Maxwell said, that probability is the true logic of the world. Why? Well, think about driving an autonomous car. And the ideal property that you want is my car never crashes. Yeah, true and false. That's logic. But of course, that's not realistic. What you want is, okay, my car can crash, but the probability of the car crashing is very, very small, and I can bound it. I can design my system so that that probability is very small. So this is what my work is focused on, and this can be used to describe properties such as safety, reliability, with probability theory and using probabilistic properties, but it can also be broadened to focus on resources, energy usage. So it's not just probabilistic, but also quantitative properties that you can express using expectations, expected rewards. So we have a specification. That specification now has to be probabilistic, because I want to be able to talk about the probability of something working or not. So here you have an example of an airbag controller. Now, how do we do it? Well, what we do is we resort to the power of abstraction, which is really derived from mathematics. So if I take a computer program, but it could also be a protocol standard, this program can then be abstracted using mathematical means into models. And these models would then also abstract the probabilities and can be parametric. So examples of models are transition systems or automata, but you can also have automata which are labeled with clocks, because sometimes you need to count time, so they would be timed automata. And of course, what we now need is models for these things, which are neural networks. So these are the main components of AI systems. So modeling is then the process of a rigorous mathematical abstraction that abstracts enough, not too much and never too little. And in my world, I've worked with Markov chains and various variants of Markov chains and Markov decision processes and different types of stochastic processes, stochastic games. Now, for verification, it is being able to do the proof for the model for a given specification, but that proof is run by an algorithm. So it's either a numerical scheme or a statistical scheme, all founded in mathematics and probability theory, but also drawing on techniques from computer science, symbolic computation in particular. But I also broaden this towards synthesis. So this is the kind of holy grail. What we want is to be able to derive something that is correct by construction. It's correct by construction. It can be a protocol, can be a policy, can be a strategy. And this is something that I think Turing hasn't thought of. Okay, it's just something that the field has evolved towards. So this is the basis, and with this, I have been working, with my team and various collaborators on a probabilistic model checking system called PRISM, which was released in 2001, and it has been used to actually find genuine flaws in real-world systems and also sometimes fix their errors. And I'll say something about that. Now, what is PRISM useful for? Okay, so because PRISM deals with probabilistic models that are verified against probabilistic properties, what it can do is can help you do worst-case analysis. So worst-case expected time, for example. It can help you find flaws in protocols, and I will show you some examples of that. It can be used to validate a hypothesis. So we have built models with biologists, and then we used model checking, say computing various trends parametrically to actually confirm or refute a hypothesis. It can be used to optimize designs, because these models can be parametric, so you could leave out some parameters, for example, and find the optimal values of the parameters. And you can build a model which is entirely data-driven and do analysis on that. Just look for patterns within the data. And finally, as I've mentioned, I'll also show you some examples. It can be used to synthesize, generate a policy which is correct by construction because it's guaranteed to satisfy a property. And there are PRISM demonstrators for all. So PRISM, okay, it's been 20 years in development, 96K downloads, but also there are over 500 papers that are written by external people outside the team. So there are literally hundreds of contributors to the tool, including the tool's code base, because the tool itself is released open source. I will not have much time to tell you about it, but I'll just give you some examples to show you the range and then what we've learned, so what these tools are useful for and why it can do analysis in a better way than alternative methods. So I'll start with the very first model that we did, which was an absolutely huge model. It's a model of a Bluetooth protocol. So I didn't have a bit of code, but there was a protocol standard, and we focused on a small part of that protocol standard, which was device discovery between two devices. Now, that device discovery relies on frequency hopping. The protocol itself, where it runs, it follows a particular pseudorandom sequence. And what we were able to do is build the very first detailed model of that protocol. And because of its complexity, the protocol, the model had 17 billion initial configurations. So those of you who work with simulation, you just can't do anything with simulation. But with our power of abstraction, we were able to construct a model and compute that the worst case expected discovery time is over 5 seconds. That's just two devices. So this is unusually large. But it's not just computing that value. We were also able to pinpoint a particular combination of the frequencies that gave you that value. Now, it is true that that combination doesn't occur very often, but if it does occur, it will slow down the protocol. So that's one example. Another example was a smart grid energy management. So this is a system and a protocol that was proposed and it was analyzed by people for randomized demand management. So the idea is that you have a group of homes and they can get energy from the grid, but perhaps also from solar, wind, etc. And the authors analyzed the protocol using simulation-based methods, but then they didn't think of allowing the clients to behave in an unselfish way. So they just missed the fact that these homes are actually autonomous. And when we modeled the protocol, we modeled it using stochastic games. And in stochastic games, clients can cheat. And we were able to find and then fix a flaw in this protocol just by applying a different abstraction and again, computing, finding the corner case. Now, one more example that I have is from robotics, but now think that you are trying to send a mobile robot to the moon. Now, you know that it has to work reliably, but you also know that it will have limited power. So what do? You know, perhaps what you can do is you can switch off some functions in order to preserve the power, of course, when it is safe to do so. So what we were able to do here is we were able to build models and then do an automatic analysis against multi-objective properties, multi-objective, because one is to minimize power usage and another one is to improve, you know, the probability of getting to the target. So I think these are sometimes conflicting. Now with this, we could do the trade-off analysis and also generate strategies that are similarly correct by construction, because they will just switch the localization on and off. They will switch it off when, for example, you know that you are a reasonable way off the target. Okay. Right, another example is, say, from autonomous driving, but just to show that PRISM models do not have to focus on hardware or, you know, software. What we also did in this case is we modeled the cognitive ability of a human. There is an approach, a framework called ACT-R, which was devised by psychologists, and we used elements of that and developed an integrated model of a human, some cognitive abilities of a human and a driver, in order to then generate correct by construction policies that produce this advanced driver assistance optimal control. So, you know, this is synthesizing policies not just for the car, but taking also, say, humans' cognitive abilities, including memory, but also perhaps how tired the human is. And finally, I will finish with DNA programs, because we were also able to debug a DNA program. And this was done in a model which combined PRISM with a Microsoft tool called DSD, and it was a very small logic gate, transducer gate, which was devised by Luca Cardelli, and it had a flaw. Now, to be honest, Luca Cardelli realized that there was a flaw, and he worked out where that was. But what we did with this, and we were able to confirm this through PRISM, and precisely pinpoint what was wrong. So that's very similar to what we do with debugging, but now it's debugging of DNA programs. Okay, so I'll just finish by showing you what we did where we could not use Prism. We could only use Prism for some small components of that. And what I'm showing you here is a pacemaker. We built a model of a pacemaker, which is, a pacemaker is a system that has to count time, so it's a timed automaton, and also has stochasticity. So with Markovian probability assumptions, we were able to build the protocol. We had also a model of the heart, the electrical conduction of the heart. We analyzed the system in closed loop, and we were able to analyze basic safety properties, which is that are always between 60 and 100 beats per minute. But further, we were also able to generate optimal timing delays between the artificial beats, and these were optimal for a specific ECG pattern for a given patient. Okay, so that's one example, and another example is from DNA. So I told you that DNA computing was like computing with soup, but in fact, people are already working on molecular computing, which is localized computation, in a similar way to the way that the logic gates behave. What they do is they take these tiles, also made from DNA, and my collaborator, Andrew Turberfield, actually does the experiments for that. Now what you can do is you can print what they call molecular walkers on this DNA tile. So we did a model of molecular walkers with Prism, but what I'm showing you here is actually a Markov chain model, which we developed with the physicists. It was analyzed with Gillespie simulation, and we used it to predict and validate various hypotheses of the physical process of DNA tile folding. So with this, okay, I've shown you only 5 examples of Prism, 2 examples outside, but I haven't said anything about neural networks. There is a whole separate lecture for that, and that lecture will also connect to probability, but we connect it with the Bayesian probability assumption through a concept known as a Bayesian neural network. So what I now need to do is to develop, models and probabilistic models for these neural networks. And what's my focus for this from the applications point of view? I'm sticking with autonomy, and the example there is actually an airborne collision avoidance system. So VCAS, ACAS, this is a real protocol. This is not for human-driven aircraft. This is for autonomous aircraft. And what it does is it performs collision detection, and it uses a neural network, an actual ReLU neural network. Why? Because if you think of an aircraft and a potential intruder, to try to analyze the different condition is combinatorially very complex. So they thought, well, we've got a lot of data. We can train a neural network, and that neural network will then produce, not specific guidance, but what is called as an advisory. An advisory says, I think, you might be in danger here, do something. So we have worked with this neural network using a Bayesian neural network, and we were able to compute safety guarantees, probabilistic safety guarantees for this protocol in a combination of a numerical and statistical way. So that was my last example, and Okay, I hope I've shown you what PRISM has been able to do, and also I've hinted what more we need to do. So, you know, if anyone wants to work on these topics, you are most welcome. I will not be able to solve these without other people's help. But as you can see, there is lots that needs to be done. Model learning, more on, say, human-like decision-making and team collaboration, etc., and neural networks. And I will just finish with a personal tribute to connect to CWI. This is Jaco de Backer. I'm personally very grateful to Jaco de Backer because I was a junior academic, just finished my PhD at a time, and he invited me to CWI, where I worked with people on the metric semantics for Mazurkiewicz traces. I think what Jaco de Backer himself was recognized for, and so I've put it here, precise and rigorous mathematical style. Precision and rigor is something that we have to use in all the abstractions and in all the constructs, because if you focus on safety, you really want to make sure that these guarantees are actual, true guarantees. So since Jaco de Backer's time, and you know, even since I started as a PhD student, concurrent systems have changed beyond recognition. This was even before the time of PCs. Now we have massive parallelism. Now we need to worry about neural networks and errors in neural networks. But the need for precision and rigor in defining the semantics has not diminished. So thank you. And thank you to my collaborators as well. So.
I think there's time for one or two questions. If you have a question to Marta, please wait for the microphone. So maybe
Worth just pointing out that de Backer was a PhD student of Van Wijngaarden.
No question. Comment. Okay. Another question, maybe.
You said, I got the impression you said that PRISM is not, in its present form, or it needs more work to be used in online real time. Can you, so in real time autonomous applications, how can you make any statements about that?
Okay, so I think it really depends on the time scale. So PRISM-generated policies, offline PRISM-generated policies, were used in actual robots. But I think the computational efficiency of policy generation is just not there. I think the trade-off, as you can imagine, is between optimality, because if you really need optimality, then you have to pay the computational price. And I think for what we do in online applications, it's always some kind of trade-off or some suboptimality that you can get away with. Yeah, but I think so there are some types of, for example, what we couldn't use PRISM for was this full pacemaker with a closed loop, because we had to have, for the heart model, we had to have more general probability distributions in the heart, and also the delays. The timing delays were also more generally distributed.
Okay, thank you, Marta, for a great presentation. Yeah, we talk a lot at CWI about the synthesis, the synergy between mathematics and computer science, rigor. Well, all of you here in this room are talking about this. it makes clear, if you apply such rigor, that it has a very broad range of possible important applications. Thanks for this. I'm very happy we record all this, because I think our field could, well, you're an ambassador to our field. So I'm very happy that we have been able to award you the prize. It is now time for a bit of leisure. We have a break of half an hour, so I invite you back to engage with one another. And we'll make sure you'll be back in time for the next part of the ceremony.
I've been catching love off a bat, boy. Running from your love, that's what this trap for. Fucking every bitch and never tell them no. I'm pushing be that black and white Oreo. I've been catching love off a bat, boy. Running from your love, that's what this trap for. Buying niggas bitches from the corner store, though. Why you wanna do that? I don't need it. I'm like LeBron James in the finals. We 1400, just like a minor. I'm yelling freebie bitch with the signers. 15 main hoes cause I'm undecided. I'm kicking shit karate, ooh. I'm serving bricks somebody, ooh. For the bitch catch a Charlie, ooh. Gucci flip-flops and joggers, ooh.
In the whip on a Tuesday night with the music high, and you by my side. Top down and the moon is high, and the mood is right, and you by my side. Conversations, electric emotions, sprinkle with a little bit of sex, and it's a potion, yeah. Late night bodies aching, mental stimulation, sprinkle with a little bit of sex appeal, and it's a moment, yeah.
Feeling fly tonight, yeah, yeah. Going with the motherfucking vibe, yeah. It's going down tonight. Don't you leave, don't you move, bada bing, bada boom, right you.
Late night conversations, electric emotions, sprinkle with a little bit of sex, and it's a potion, yeah. Late night bodies aching, mental stimulation, sprinkle with a little bit of sex appeal, and it's a moment, yeah.
I was scared of dentists in the dark. I was scared of pretty girls and starting conversations. All my friends are turning green. You're the magician's assistant in their dreams. Ooh. And I call my star. Baby, running down to the riptide, taking away to the dark side. I wanna be your left-hand man. I love you when you're singing that song, and I got a lump in my throat 'cause you're gonna sing the words wrong.
Some things look better, baby, just passing through.
And I think it's gonna be a long, long time till touchdown brings me round again to find I'm not the man I think I am at home. Oh no, no, no. And this is what I should have said. Touchdown brings me round again. Well, I thought it, but I kept it. No, no, no.
can't believe it. You wouldn't believe me. Fuck all of your reasons. I lost my shit, you know I didn't mean it. Now I see it. You run and just repeat it, and I can't take it back. So in the past is where we leave it now. So there you go. Oh, can't make a wife out of hoe. Oh, I never find the words to say I'm sorry, but I'm scared to be alone. You cut out a piece of me, and now I bleed internally. Left here without you, without you. And it hurts for me to think about what life could possibly be like without you, without you. Oh, oh, ah, oh, oh, ah, oh, oh, ah, oh, oh, ah, without you, without you. Oh, oh, ah, oh, oh, ah, oh, oh, ah, oh, oh, ah, without you, without you. It's gonna be harder on my own, even harder to let you go. I really wish that we could have got this right. So here I go. Oh, can't make a wife out of hoe. Oh, I never find the words to say I'm sorry, but I'm scared to be alone. So here I go. Oh, can't make a wife out of hoe. Oh, I never find the words to say I'm sorry, but I'm scared to be alone. And it hurts for me to think about what life could possibly be like without you, without you. Oh, oh, ah, oh, oh, ah, oh, oh, ah, oh, oh, ah, without you, without you. Oh, oh, ah, oh, oh, ah, oh, oh, ah, oh, oh, ah, without you, without you. It's gonna be harder on my own, even harder to let you go. I really wish that we could have got this right. So here I go. Oh, can't make a wife out of hoe. Oh, I never find the words to say I'm sorry, but I'm scared to be alone.
You feed my heart and embrace my soul. No one's ever done so. Without your presence, without your hope, the right places feel so wrong. They want me high, but I feel so low, and only you can change that. They miss my smile, but I can't let go. I need you in my life, babe. I feel cold in the heat, caught in a dream when I'm without you. Stretched out on the ground, leave me here, 'cause I found me lost without you. You feed my heart and embrace my soul. No one's ever done so. Without your presence, without your hope, the right places feel so wrong. They want me high, but I feel so low, and only you can change that. They miss my smile, but I can't let go. I need you in my life, babe. I feel cold in the heat, caught in a dream when I'm without you. Stretched out on the ground, leave me here, 'cause I found me lost without you. we choose to just release and throw our hurt into the sea. I believe in letting go. Control is a losing game. Power's an illusion, now I know. I believe in letting go. Trust leads to bravery. Love is the only way. This is letting go. This is letting go. Love is the only way.
Decisions as I go to anywhere I flow. Sometimes I believe, at times I'm rational. I can fly high, I can go low. Today I got a million, tomorrow I don't know. Decisions as I go to anywhere I flow. Sometimes I believe, at times I'm rational. I can fly high, I can go low. Today I got a million, tomorrow I don't know. Stop claiming what you own and think about the show. We're all playing the same game, waiting on alone. We're unknown and known, special and a clone. Hate will make you cautious, love will make you grow. Make me feel the warmth, make me feel the cold. It's written in our stories, written on the walls. This is our call, we rise and we fall. Dancing in the moonlight, don't we have it all? Decisions as I go to anywhere I flow. Sometimes I believe, at times I'm rational. I can fly high, I can go low. Today I got a million, tomorrow I don't know. Make me feel the warmth, make me feel the cold. It's written in our stories, written on the walls. This is our call, we rise and we fall. Dancing in the moonlight, don't we have it all?
The cars run so fast. We're sitting on the sidewalk, watching people talk. We're all alone. I know that we're doomed. Someday we'll bloom. I'm here just for you and you for me. That smile on your face just tells me to stay. Maybe it's not.
Oké. Hij doet het. Hij doet het. Hij doet het. Oké. Oké. One way or another, I saw many smiling faces. People coming back, they didn't notice I was looking at them. I was carefully sensing the mood, and the mood is good. Or well, no, good. We go to the second part of this Van Wijngaarden ceremony. And you can imagine, we know already the laureate to be, Susan Murphy. And Peter Grunwald will provide the eulogy, the laudatio. The floor is to you, Peter.
Okay, well, good evening, everybody. Can I get the next slide? Which should be, or should I do it myself? Okay, good. Wait, this is. I see different. I see something very different here. Wait. The green button. Oh, this is new. Good.
Oh, this is pointer. This you push, and this is the next. Yeah.
It's niet goed. This is not right.
So this is. Wait a second. No, you cannot do it. Only. Why should we should point it somewhere, and this I don't know where to point it. Yes, but this is forward. This is backward. No. This is forward.
This is forward.
Yes.
Nothing happens.
But I don't know which direction.
And this looks very different
no,
here.
you cannot. This is somebody else.
Oh, okay. Yeah. This is her.
You
Yeah.
cannot,
Okay. Yeah.
They're working on it as we speak.
Ah, good.
There's also something out there that is kind of. Translating them. It's not your fault, Peter.
We have a great idea. They need to install Prism.
They didn't test up front. Was there any chance that it wasn't? No, we know.
It's Murphy's Law, I guess. Kan het ook zonder, hè? Kan het ook zonder.
Is dat net weer aan het
Nee, ik had het zeker even gefoten.
Ja, ik zie iets van de glimps van dat soort dingen. Maar ze hadden de verkeerde presentatie voor staan. Zonder is Ja. Ik wacht even, anders gaan we het zonder, ja? Hoeveel tijd hebben jullie nog nodig? Want anders gaan we zonder slides verder.
Like I go to, but I'm out. I can't do anything. I can't even have an apple. I can't go with anything alive back, you know, because they have the police. It's very sad. Right, for life. Yeah, and if you get caught, then you're stuck there half the day. It's just not worth it. It's not worth. It changed going backwards. It's quite clever. Yeah, because every now and then I realize, oh, I actually see us. But then I lose us again, and then I see us again, yeah.
Yeah.
Good. As I said, Murphy's Law. So Susan Murphy was born in rural Louisiana, and though her life can be described as a random walk, or maybe not so random walk with a drift towards the northeast, There's still something southern about her. I think if you listen very, very carefully, there's a slight southern drawl. I heard it's drawl, not twang. I hope that's correct. And in fact, when she moved north first from Louisiana to do her PhD at the University of North Carolina at Chapel Hill, I hear she was complaining about the cold weather. But that can't have bothered her too much, because afterwards she actually wanted to do a postdoc in the Netherlands, where it's much colder, with Richard Gill in Utrecht. Richard Gill is here in this room. He had actually just left the CWI to become a professor of statistics in Utrecht. She stayed there for about 9 months and then went back to the US, but had several other prolonged visits in the 1990s to the Netherlands. And then when she went back to the US, she actually embarked on a stellar career, where in 1997 she moved to the University of Michigan, where in 2014 she became the Herbert Robbins Distinguished University Professor of Statistics. And in 2017, she moved to Harvard. In the meantime, she had obtained a MacArthur grant, actually a MacArthur Fellowship, the so-called Genius Grant. I guess that says enough. And she is a member of both the National Academy of Science and the National Academy of Medicine in the United States. And I think there are not many people in the intersection of those two sets, but Susan is. She has received the Guy Medal in Silver from the Royal Statistical Society, the R.A. Fisher Award, and she is a former president of the Institute of Mathematical Statistics. Well, I could go on like this, but I won't. One more thing about her life is that she also is an avid ice hockey player, I think at least 3 times a week. Is that correct? So that is at least, so that's really astounding, I think. So, but now let's talk a little bit about her work, which is she's here after all. So we had from Alan to Marta, and now we go from Sir Ronald to Susan. Susan is originally a mathematical statistician, but I should emphasize here that she's not just that. She's actually at Harvard. She's a professor of statistics, but also a professor of computer science, machine learning. And in Michigan, she also had an appointment as professor at the Department of Psychiatry. But she did start out really as core mathematical statistics, although even then there was a medical component to it. So to get an idea of what that was all about, let's go a little bit into history again. So if statistics has something like a real founding father, it would be Sir Ronald Fisher, who really shaped our modern thinking about statistics in the 1920s and 1930s. And 2 of the key concepts that come from him in our modern form is likelihood and randomization. So Susan's work has, to a large extent, at least her early work, been on an extensions of this idea of likelihood, and that's connected to another Sir David Cox, who actually died only at the age of 98, only this year. So Sir David Cox wrote in 1973 a paper on, I think it was called Regression and Life Tables, and that paper completely changed the field of medical statistics. It did so by basically extending Fisher's idea of likelihood to a different setting, where hitherto it was thought that it would be far too complicated to use it. And this is all about the probability that when you're in a group of patients that you get a certain disease or not. So this has saved countless lives, this paper, but it also really attracted a lot of mathematical interest, because it was really just asking for more mathematical analysis and extensions. And this was what Susan's PhD thesis was about. So in the original Cox model, you could, to determine probabilities of getting a disease, you could take into account things like a patient's age or gender or blood pressure, features like that, but they were static. They were not allowed to change in time. But with patients, you usually look at things changing over time, so you want to deal with covariates, features that can change over time. And Susan was one of the first people who worked on that in her PhD thesis. Then she went on to work with Richard Gill, who was one of the world's foremost experts on the mathematical aspects of the Cox model. And he gave her a problem, which she then solved on her own, and it led to a single-author paper in the Annals of Statistics, so published As Richard told me, this is the time when it took 4 years to get a paper in the Annals of Statistics. You did the work in 1990 in Utrecht, and in 1994 you got a single author paper in the Annals, which of course later you became an editor of the Annals. Then Susan moved on to do a lot of other fundamental contributions, and I'd like to mention one of these in particular, because it's again related to the concept of likelihood. It's now about a different extension, but related extension, to use likelihood in models for which it seemed, again, far too complex, very complex, high-dimensional models. And I'm mentioning explicitly this one. I have to admit there's a little bit of cultural bias here, because her first paper on this was done together with a Dutchman, Spinoza Prize winner Aad van Wijngaarden, who's also in this room. So this happened around the year 2000, and afterwards Susan went on to do some more applied work, where she came up with microclinical trials, and this is again related to one of the great innovations of Ronald Fisher, namely the idea that randomization is fundamental to learning things in statistics. So we all know about randomized clinical trials where some patients get a placebo and others get a treatment. Right? You randomize them into one group or the other, and then you see what happens. And originally that was basically it. But so what Susan initiated was to look at a basically per patient basis, where each patient has a different treatment regime, and you keep adjusting and basically experimenting with the patient as time goes on, and keep on randomizing, like, should I do this treatment to the patient or that, and so on as time goes on. So this has very important applications for chronic diseases like alcoholism or other drug abuses, but also chronic heart diseases. In more recent years, she has actually extended this to basically doing randomized trials with your mobile phone, with an app, mobile health. But in all this applied work, apps, the beauty of mathematics, in her own words, I think is still central, and I think that's Susan Murphy for you. Thank you.
Susan. And Marcel, can I invite you to the stage?
In the first place, Susan, congratulations with this fantastic prize. I think Peter explained it very well. Your work is stellar. As a medical person with a medical background myself, I had heard from you, which is fantastic because I didn't hear from many other mathematicians, to be totally honest, but that's my mistake. I'm learning a lot tonight. And indeed, your work in chronic diseases is fabulous, because there's not that many people who work on chronic diseases because it's not so sexy as acute diseases. But as the group of people who are affected by these conditions is growing, it is extremely relevant. There is also one other thing I'd like to highlight, and that is that more and more people come to the realization that if you want to make real fast progress in science, you often have to find a spot on the interface between different disciplines. And that's a term that has become very much in fashion, multidisciplinary, so everybody's talking about, but actually you are doing it. And that's one of the reasons your research is so extremely successful. So I am honored to give you this fantastic prize today. As we've seen, it comes with flowers and also with, we didn't highlight that for the previous prize winner, the CWI sweater. And I have one myself, and I can actually advise you to wear it in the train, because then students say, he is really smart if you are wearing it. So that's why it's very popular with me, at least. So congratulations.
My t-shirt, my sweatshirt. You can hold the flowers. No, this is fine.
Super smile. Okay, well, there you go. I guess you should.
Do it so much.
You give it to me.
Yeah.
Well, Susan, congratulations. And I just already explained that you have this duty, the duty to perform. I look forward to your presentation, and so all of us.
Thank you. Thank you so much. It's a pleasure to be here with all of you. Let me start my slideshow and see if it comes up. Okay. Oh, great. I'm very happy. So I'm going to talk today about some work that I'm engaged in right now, and it's quite incomplete. See what people say. First, I want to state that it's a great honor to be here with you today to receive this award in the honor of Van Wijngaarden. I was really impressed, about the fact that he connects applied mathematics to computer science, and I really like that. This is something we need to do, to have computer science have more of a mathematical foundation. And I list some of the things that I thought were really impressive, particularly being part of the team that formed one of the first computers in the Netherlands. That's impressive. That's really impressive. It's great. One of the things before I leave this slide, I want to mention something. In 1989, when I graduated from, got my PhD, I don't know if people here realize, but the Netherlands was just, everybody knew about the Netherlands. It was the place to go if you did any kind of work in martingales, in stochastic processes. This was where you came, particularly if you were interested in how you might apply these mathematical tools to health. It was the place to come. And so I was really fortunate. Some people intervened for me, and Richard let me come to spend time with him. And then I get here, and then I learn about CWI. And as a postdoc, or really I was more like, even though I had finished my PhD, I felt more like a grad student. CWI was like the castle that was on this big hill. And if you got really lucky, you too could go to the castle. This is what I remember distinctly. So, it's just wonderful to be here with all of you. It's a great honor. The kind of work I do, it involves large teams with people with a whole variety of backgrounds, and I'm going to talk to you about a particular study today, one that I do use to illustrate ideas, heart steps. And PEDGA is a human-computer interaction specialist. There's pictures of behavioral scientists, software engineers, and statisticians. Peng Liao is the person who did the development of the RL algorithm. So this work, it started with, we wanted to develop a activity coach, a mobile activity coach, for people who had just been diagnosed with stage 1 hypertension. This is a unique time in a person's life. If they're able to change their behavior and they're fortunate, they may never have to go on drugs. So it's a really unique time to change one's behaviors. And we were able to run 3 studies in which we would look to form an autonomous coach for this person. So in this case, there was an app on the person's phone, and they have a wearable tracker, and the wearable tracker tracks their sleep and their physical activity, and then there was a variety of sensors on the phone as well. I list here 3 studies. The first 6-week study, which I call it micro-randomized. I'll be clear about that shortly. And then the 2 longer studies, the 90-day and then the 9-month study, in which there was multiple algorithms running during these studies, these clinical trials, autonomous algorithms, and they both micro-randomize and personalize. And I'm going to try and make that clear in the next slides. So when I say micro-randomized, this just means that there's sequential experimentation. And in these studies, the number of times each individual is randomized, it can be in the thousands. So each individual is randomized many, many, many times. And one way in which these probabilities are the probabilities of randomization get determined. There's a whole variety. Usually it's some sort of optimization algorithm you're trying to learn about parameters in that the criterion function. At the same time, you're trying to optimize that criterion function. And in particular, one of the algorithms we used was a reinforcement learning algorithm. And from the viewpoint of health, reinforcement learning algorithms, the goal is to learn in order to personalize, experiment in order to personalize. That is the purpose of a reinforcement learning algorithm. So in the case of Heart Steps, there were 6 different intervention components designed to help a person about different aspects of their life. And we're just going to focus on one of those intervention components. And this is the one that we had the algorithm running, the RL algorithm. So in this case, the idea was to help someone be more active as they went about their daily life. Just small ideas about how they could just add physical activity to their life. And each person had 5 times. These were person-specific times, had to do with how they lived, how they ran their work, and so on, at which they might receive a notification on their phone that would give them some tip about what they might do at that moment. And you can see an example of that on the right-hand side. The content of these suggestions, that it's tailored to the sensor data coming in on the individual, so it's tailored to where they are at that moment. It was tailored to what the weather was like. It was tailored to whether it was weekday or weekend. In this case, this was a weekday morning, and it was quite cold outside. And so at each of these 5 times, you might get one of these messages on your lock screen. And the state, I give you some examples of some of the data that was used to decide whether or not to send these messages. There's a variety of different types of variables. Also, we call the treatment, that is, send a message, a contextually tailored message suggestion versus don't send one. We call it an action in this literature. And this is the algorithm's action, what the algorithm provides to the individual. And then the algorithm, in order to personalize, is provided a signal, which is a reward. And I want to hear, this was the first time we ran a reinforcement learning algorithm, and so our choice of the reward was relatively naive. It was related primarily on the behavioral science. These messages were intended to help the person in this current moment, and here, so we used a reward of 30-minute, subsequent 30-minute step count. This area of choosing the right reward to help the algorithm learn, this is really open, particularly in regards to health applications. It's an area that needs a lot of work. At the bottom of this slide, you see in blue, you see my math. My math is the expectation of the reward given the person's current state S and the action, and in this case, we're going to focus on a binary action. A is 0 or 1. I'm going to denote that just conditional expectation by the lowercase r. So during the study, the RL algorithm was intended to autonomously, no statistician is in the loop, select actions, select whether to send a message with the goal of maximizing the overall activity, the responsivity of the person over the whole duration. Now, it turns out that when you go to use reinforcement learning in these types of health applications, you actually have multiple goals that you need to satisfy. It's not like all you want to do in the world of reinforcement learning. Some people call it regret minimization. That's not the only goal here. And so you have to make compromises. And a really important point here is the need to balance within study learning, within study personalization, to between or within between study learning, because these are continual learning kind of settings in which you want to learn between the studies. Notice I had 3 studies originally, and if you roll this out, you'd have the same sort of idea. You want to learn between batches of data. So you always have to balance that goal of maximizing the reward. The algorithm has to balance that with the potential to be able to learn after the study's over. Also, from a domain science perspective, you have to be really careful. You are experimenting with people as they go about their daily life, as they go to the grocery store, as they sit at home watching TV. You can't bother people that much. You have to really be thoughtful. And we know in medicine, you really don't want to do harm. It should be do no harm, right? You don't want to bother someone for no reason whatsoever if it's not going to really be helpful. So in the second two studies, the 3-month and the 9-month study, we deployed, I'll call it, it's a generalization of a Thompson sampling bandit algorithm. It's actually a generalization in the direction of full RL, and I'll speak to that shortly. And the goal of this algorithm was to personalize. And the way we're operationalizing or mathematizing personalization is maximizing that sum of rewards, but it's subject to these very ill-posed constraints. Again, this is another really, there's open problems everywhere. We don't really know in a principled way how to balance between study learning and within study personalization. That's a problem that hasn't been properly mathematized yet. So when someone talks to you about any RL algorithm, and in particular Thompson sampling, there's always two elements to these algorithms. There's the first element is some sort of learning algorithm where you're learning some aspect, some model of the user. In our case, it's a user. These are models of individuals. We used a very simple learning algorithm. It was just Bayesian linear regression. It was a very simple form of a GP model. For the reward. Remember, the reward is the mean, the conditional mean of the reward given current state in action. The reason for this is a setting in which the signal-to-noise ratio is relatively low. You have to really trade bias and variance off as you seek to learn. This is a critical thing to do, is to adroitly trade bias and variance off. And so by using simpler models, of course you have bias, you have to, but you learn much faster and you end up with better decisions. So the learning algorithm is just an online statistical method. And then there's the second element is this action selection. That is, how is the algorithm deciding whether or not to send a suggestion, one of these tailored suggestions at any given time, 5 times a day over the whole study. And the way we do this is use the idea from Thompson sampling, and this is posterior sampling. So this is an optimization. This is an effort to optimize posterior sampling. So in this case, we have binary treatment. So what you do is, because you have a Bayesian learning algorithm, you calculate the posterior probability that the advantage of sending a suggestion in state S over not sending a suggestion. That's the difference between RS1 and RS0, the advantage of sending a suggestion versus not. You calculate the posterior probability that exceeds some threshold. I'll talk to you about the threshold shortly. Once you have that posterior probability, it's going to be very high if there's a lot of evidence that's accrued that it's worth sending a suggestion. It's going to be low if there's very little evidence that's accrued that says it's good to send a suggestion. So it makes a lot of sense to use that posterior probability and to do the randomization with that posterior probability. It'd be higher if the evidence is indicating it's worthwhile and lower otherwise. What's the threshold? So if you're in like OR or other areas and you're familiar with MDPs, Markov decision processes, this threshold, it's related to the value of next state. The difference of value of next state if you take an action versus not at this time. And what we did, because the noise level is so high in these real life kind of experimentation settings, is we built an MDP off of the first heart step study. And then we tuned it during this study. But the posterior sampling does not take into account any of the uncertainty in the value of next state. It's just, in terms of the posterior sampling, it just takes it as a bias term and then moves on. But what is the purpose of this threshold? The purpose of this threshold is to anticipate future burden, the fact that the person, if you bother them too much, they're not going to respond anymore. or in the words of psychology, habituation is a big problem. This is well known in psychology, and you need to back off. So an optimal policy, usually in these kind of settings, is one that treats, the person starts to habituate, it comes back. It's conceptually, an optimal policy has that kind of trend with habituation and dishabituation. At least that's what people believe. And that's what this threshold is doing. It's anticipating the delayed effects of sending a suggestion right now. I want to talk to you just some highlights. I'm just giving you highlights. This turns out, the whole problem turned out to be harder than we thought it would be, and I'll just talk a little about some of the things we learned. First of all, what we did was we only used a low-dimensional linear model for the advantage. So that was the main place where there's this linear model. Theta, the theta weights. F is a group of features. It includes the person's current location and other features, summaries of the person's behavior. And it's only 5-dimensional. So it's a feature of S, the state. It's only 5-dimensional. There's only 5 weights. This turns out to be a lot of weights. So we have a low-dimensional model. That is, we look at a linear combination of 5 features for the advantage function, the advantage of sending a suggestion versus not. And we put a prior on theta. In my world, priors are the same as how you initialize an optimization algorithm. That's the purpose of a prior, is to initialize an online optimization algorithm. And our priors are always informative because the problem is so noisy, you need to get sort of close to where the maximum might be. And so how did we form this prior? We formed it using the first study, V1. And I want to mention, and it gets updated. There's a first week where each person is just randomized with a constant probability at each time, and we update the prior for that person. I want to make one statement about this prior that if I get to this, it'll become important. In the first study, we saw very strong effects of sending one of these suggestions, these contextually tailored suggestions. People really moved a lot more. They more than doubled their activity. It was quite striking. So what does this mean about the prior? The prior anticipates that there's going to be a strong effect. It turns out, so this is a strong effect on average across people, not for a particular individual necessarily, but on average. Right. So so it didn't really turn out that to be the case. This prior turns out to be slightly misspecified, but I just want to make that very clear. This prior, the prior mean for theta, the very first entry in theta was the overall effect of sending a suggestion. It was strong and positive. All the other entries in theta had a prior mean of 0 because we didn't have a prior subjective bias. Okay, so what's a highlight of the action selection algorithm? So here we made a big mistake. We actually had to restart the study. So there's the posterior probability. Again, this is a Bayesian paradigm. We have theta, which is 5-dimensional, and there's 5 features of the person's current state. That's f of s. And we're looking to see what's the posterior probability that this advantage is greater than the threshold. Okay, what happens? Suppose in some states, the difference between the advantage and the threshold is close to 0, indicating that the posterior distribution is centered about 0. What does that indicate? That indicates that there's not a lot of evidence that sending a suggestion is worth it. It doesn't overcome the threshold that it's worth it. What does Thompson sampling do? Thompson sampling, the posterior probability, will send the message with a probability of 1/2. This is in a setting where we don't have evidence that it's really worthwhile to send the suggestion. And we're going to send the suggestion with probability 1/2. This makes no sense from a medical perspective. I should have realized this. Luckily, I realized it after a week. We restarted the study. also, that was the first issue, is it just doesn't make any sense. You don't just send suggestions that you don't have any evidence of them working one half of the time. And also, we got to remember, we have to be able to learn between studies. You have to be able to learn. So you have to have some low-level exploration or randomization all the ways in order to learn. So how to manage this, I have no idea how to do it in a proper way, okay? This is what we did. So what we did, you see my little graph, I drew it. So the x-axis, the horizontal axis, is the posterior probability, the probability suggested by the algorithm. This is the probability you should send a suggestion. As you see from this curve that I drew, the new probability is between 0.8 and 0.2. If the posterior probability is 0.8 or higher, you just send the suggestion with probability 0.8. If the posterior probability is 0.5 or lower, you send the suggestion with probability 0.2. I mean, this is like we stopped the study. We had to do something. Everything was a crisis. Anyway, so how do we determine these probabilities? Well, the upper probability is 0.8. We know we need to have some exploration. We can't send a message all the time. If we send it all the time, we won't be able to learn when it doesn't work. So 0.8 is less than 1. And also, we're concerned about habituation. 0.2, where does 0.2 come in? 0.2, again, we can't be in a setting where we never send a message. We won't learn when it's useful. But even more importantly, and this is something that's very interesting to me, in some areas of medicine, stochasticity itself can have a therapeutic effect, particularly in the behavioral sciences. Very interesting. And we haven't figured out how to think about that properly. Anyway, that's why we chose 0.2. Okay, so, look, like total lack. So this is an area, I want to emphasize, this is part of the reason, this is an area that's completely open. It's completely open. Okay, I want to show you some results. So this is we had a number of users there was 91 individuals in this study. We had a number of individuals who had patterns not quite like this, but similar. And this is a very exciting pattern. So this study, let me just tell you where these studies went on. They went on at Kaiser. This is a health maintenance organization in Seattle. All of the individuals in this study had just been diagnosed with stage 1 hypertension, and they were asked to come into the study. This is one individual. This person came in mid-November 2019, right before the pandemic. Seattle closed down end of March in 2020, and you can kind of see actually this individual's behavior sort of compresses during this period when the pandemic just first closed down. And then the individual leaves the study in August 2020. So what's the height? What do the heights of the dots mean? The heights of the dots it's the learning algorithm's prediction of whether or not the person is going to be very responsive. So it's a posterior mean divided by the posterior standard deviation. So it's like a signal to noise ratio. If the dot is above 0, that means the accruing date is indicating in that person's current state at that time, it's forecasting that it's worthwhile to send a suggestion. If the dot is below 0, the algorithm is forecasting in that state at that time that it's not worth it to send a message. Okay, so you can see it was very exciting when I saw this because when the person was engaged, so what's engaged here? Engaged means they're looking at the app and they're tracking their physical activity, all of their own volition. So this is a person who's looking at their behavior. These are the blue dots. The red dots blue dot means yesterday I, the user, was tracking my behavior. A red dot means yesterday I did not really look to track my behavior. And we see this picture and it was extremely exciting because you look at this and you think, this is fantastic. Yeah. We're going to get into truth in advertising shortly. But how does that mirror in the randomization probabilities? Well, it should mirror, as you might expect, is that when the height of the bar is above 0, you have with higher probability you send a suggestion. When the height of the bar is below 0, with lower probability. And so that's exactly what you see here. It's clipped above by 0.8 and 0.2, like we had talked about earlier. And you see those probabilities varying in alignment with the forecast. So essentially, that's what the learning algorithm is doing. It's constantly forecasting if it's worthwhile to send a message, and then the posterior sampling sends messages to the individual according to that. And indeed, I've just replicated those 2 slides. This is what we in our group, in our lab, this is what we're suggesting to the health field, the behavioral health field. This is what we mean by personalization. Personalization is when you have an algorithm that processes accruing data, makes a forecast, and then you, with probabilities that depend on that forecast, you provide the action, the suggestion. You have this mirroring. Okay, I'm not going to do this first analysis. I'm going to do a second one. I'm going to do the second one. And so I showed you that user, and the data from that user. And we have a number of users with data like that. And it was extremely exciting for me. Let me just go back to that slide. So I looked at this slide, and I thought, first of all, we're using a reinforcement learning algorithm, which is quite sexy in today's world. And I look at this and I think, whoa, man, this algorithm very quickly learned on this user that when they were looking at the app the prior day, it's worthwhile now to send them a suggestion. I was very excited. You know, in the US, we're quite entrepreneurial, and I have to bring in money to support my lab. Yeah, I'm thinking, man, I have it made now. Right. So, but we also know in AI that we've had a lot of fiascos. It's very easy to overpromise what we're doing, right? And we don't want to overpromise here. Okay. So here's that same picture I showed you. And the question is this really evidence that we personalized? That's the question. That's the task we had ahead of us. And we had a whole variety of analyses. It would take me it's a whole talk about different ways to triangulate on whether or not the algorithm is personalizing on average for people, or even personalizing potentially for this user. And I'm just going to show you one approach we used to look at this, and it's quite, I found it quite, it really opened my eyes. Okay. So this blue curve is that user's posterior mean for the interaction of engagement. And you can see the blue, that's exactly that particular user's, that's real data for that user. And you can see the blue curve on the far left starts out at 0. That's because the prior mean for engagement, the interaction of engagement and sending a suggestion was 0. That's why all of these curves start at 0 on the far left. So what are all these black curves? There's 2,000 black curves. And so what we did was we formed a model. For each user had their own model. That was part of the learning algorithm. And we take that model and we strip away, at each time point, we strip away the mean of the reward given state and action. And so we end up with state and a residual, because we take the reward minus its mean. So we have state, residual, state, residual, state, residual, for the entire period of time that person is in the study. And then we bootstrap those state residuals. So we bootstrapped them, we took a random sample, and we ran, for one bootstrap sample, we reran the algorithm under a particular ground truth. And the ground truth we reran the algorithm on is the ground truth of no effect of engagement. So every one of these black curves is a pseudo individual, same sort of error properties of this particular individual, for which the ground truth we know is there's no effect of engagement. So at the very beginning, what you see is that this blue curve, okay, so it's greater than 0, but it's well within the mass of the black curves. What does that say? This is a stochastic algorithm. This algorithm, by just stochasticity alone, could give you this signal of there being an effect. And it's just totally spurious. It could be totally spurious. It's well within the mass of the blue curve, the black curves. But as you go along towards the end, finally, maybe there's some evidence that we're actually personalizing. So again, going back to that picture, it looks like we're learning. It looks like the algorithm's learning because it's repeatedly forecasting over and over again. It gets more data. It keeps forecasting that it's better to send a suggestion when you're engaged. But it's only towards this in May, early June, that you really see enough evidence has accrued so that the blue curve starts to drift higher than all the bootstrapped versions of that individual. So now when I put this in my grant, I have to explain this. This is a case where you really needed a good bit of data before you began to have a lot of evidence that there was some differential effect. This is where we're going. So So I think of like working with Kaiser. There were 6 intervention components in Heart Steps. Again, like I said, they were targeting different parts of that person's life. Another component, a 7th component, would be an RL algorithm. It's part of the treatment now. An algorithm is part of the treatment. And this is a setting in which you have to continually learn. You have to continually update the algorithm as time goes on. So this is where we're really moving, is how do you warm start each algorithm for each person and then continually update that algorithm through time. Thank you.
We should have time for a question. And again, microphone is here. Linda.
Thanks very much. That was absolutely fascinating, and I understood almost all of it. Can you go back to the slide with your black lines?
All those black curves?
Yeah. So I don't want to be a damper, but on the right-hand side of this diagram, the blue dives into the black again.
Right, because the interaction starts, the evidence of an interaction dissipates. Look, go back again. See how, think about this is COVID, right? And now time is going on. Well, I'm conjecturing, right? This is me conjecturing. But now the person starts to become more responsive. It's in July. They become responsive no matter what. So of course, it's not, you don't need to take into account. So the need to take into account engagement may not be a constant thing. And in fact, we know humans are non-stationary, right? I mean, really. And the reason why we're non-stationary, in my opinion, is because we don't have good enough sensors to sense everything that's going on in your head and to sense everything that's going on in your surrounding. So something might have happened in this person. I have no idea.
Susan?
Could be chance. Yeah.
Thanks very much. It is, you said it's completely open.
Yeah, this is a very open field.
All the way from Louisiana to Boston, you have explored and you will continue to explore. Thanks for this inspiring talk.
Yes.
This brings us to the end of the celebration of science and the celebration of mathematics and computer science. Thanks all of you for being present here to do justice to Marta and to Susan for receiving the prestigious Van Wijngaarden Award. I invite you now to enjoy each other's company for a drink and hope to have a safe trip home.